2 years ago, the Nobel Prize of Physics has been given to Michel Mayor and Didier Queloz. They discovered in 1995 one planet around a solar-type star. This has been the first of this kind to be discovered. Since then, astronomers have discovered many other systems of planets. And what is interesting is that these systems shows several planets in apparently very stable orbits around their stars. Until recently, celestial mechanics had to study only our own solar systems, the systems of planets and the systems of satellites around these planets. What's remarkable is that this system is 5 billion years old. And what means that it is relatively stable. However, we know that in the inner planets, if we look a little bit, the span of their orbits for the next 1 billion years, we see that the possibility of these 4 planets to have a close approach of 2 of them is not discarded, and a cataclysm may happen in the inner solar system. But it will be necessary billions of years for such an event. Now, we have to, if we look at the periods of the outer planets, we see that they are listed here. Jupiter has a period of 5 years, Saturn 9 years, Uranus 19, Neptune 30. If we look at these periods, the numbers given these periods, we see that they are very close to some rational numbers. For instance, Jupiter to Saturn is 2.5. Saturn to Uranus is 1:2. Uranus and Neptune is 2:3. However, if we combine these frequencies, making the proportion, for instance, 2 times the mean motion of Jupiter minus 5 times the mean motion of Saturn, we have a number that is far from 0. So these systems are not resonant, but they are not very far from resonances. And these are some consequences, as we can see in this figure. This figure shows the chaoticity in the outer solar system. We keep Jupiter, Uranus, and Neptune exactly where they are, and we initialize Saturn on a grid of different initial conditions. And we see that in this picture, if I put Saturn in one of these red regions, it would be destroyed very quickly. If in the dark ones, we would have some chaos, we would have some instability, but it would not remain there, but it would take some time before disappearing from there. And if I look at the real Saturn, I see that he is very close to a resonance. He is very close to the 2-5 resonance with Saturn, but it is in the safe region. The white region here is a region where the spectral numbers are very small, indicating that the motions are substantially regular. Let's look now the exoplanets. Let's start with this very interesting example, K2138. In this case, the relationship of the periods from one planet to the next one is always very close to 2/3. And if I make the combination, 2 times the mean motion of one planet minus 3 times the mean motion of the next one, we have very similar numbers. Look at the right. Well, the first one is 2.6 degrees per day. But if you look, the other one is 2.48, 2.48, 2.49. What this means? This means that if I, instead of considering an inertial system of reference, if I consider a rotating system of reference, and if I make the system rotate exactly with the velocity, the angular velocity indicated by these red figures, so 2.48 degrees per day, the system would be exactly periodic in this system. So in this rotating system, when the second planet gives 3 orbits, the third one will run exactly 2 orbits, and so on. 2/3, 2/3, 2/3, and 2/3. I would have a system. The system is very close to a periodic solution. Let us continue. We have discovered many resonant chains with 3 or more exoplanets. In this table, you can see I put on the name of the system. In the second column, the number of planets. When like the first one, I put there are 4 planets, but only 3 are in resonance. The other one is not, and so on. And these resonances are indicated in the next column. You see, for instance, the system that we have discussed just before, 322, 322, 322, 322, in a red box on the right side. No? This is one of the systems that are there. The others are different resonances, but always in chains, except one of them, Kepler 90, in which we have 2 chains. One chain with the inner planets and one chain with the outer planets. In this case, we have 8 planets, and 5 of them are tied by commensurabilities. The other system that is very appealing is GJ876. GJ876 has been one of the first resonant planets to be discovered. We have already about more than 20 years of observations. So we can have very good periods, determined. And we see that if I consider the 3 outer planets, they are in the rate of 1 to 2. The period of the second is half of the period of the third. The period of the third is half of the period of the fourth. So it seems that they could be in the Laplacian resonance. If I take the frequencies of them, the mean motion of the second planet minus 3 times the mean motion of the third planet plus 2 times the mean motion of the fourth planet, the result's close to 0. In the formula on the bottom of the figure, I have used indices that do not correspond to the names on the table, because I just considered the 3 ones that are in resonance. Let's continue with it. What is interesting is that it seems to be in a periodic solution. This periodic solution, that's sometimes called a de Sitter solution, we have the 3 planets are in, for instance, the first one as period 1, the second one as period 2, the third one as period 4. So that when I compute n1 minus 3, n2 plus 2, n3, the result is 0. But more than that, if I compute the longitudes, sorry for the wrong symbol in the figure. PowerPoint sometimes does that. So we have the longitude of the first satellite minus 3 times the longitude of the second satellite plus 2 times the longitude of the third satellite. In the de Sitter periodic solution, it would be equal to 0. Sorry, equal to pi. But in this case, the result is very close to 0, and there is some discussions if the system can be stable or not. There are papers in which it's saying that the only possibility of having full stability, the full equilibrium solution of the Sitter in a stable situation is when the combination of the angles is equal to pi. Others says that it can be stable also when it equals to 0. This is a problem that we have to solve in the next years. What is interesting is the following. Okay, I have told you that in fact the angle lambda 1 minus 3 lambda 2 plus 2 lambda 3 is not equal to 0, but equal to minus 7 degrees. So we have not exactly the condition for the periodic solution of the Sitter. And when we look at the stability along this, the Sitter solution, this has been done by Marty and collaborators in a paper published some 5 years ago. We see that the region that corresponds to the libration of the resonant angle around a constant value is very thick. Is very thin. The width of this figure, that is the blue and green regions, is about 1 degree. The same amplitude is about half degree. 1 degree is the width. Sorry, 1 day of period. I am talking about periods. Excuse me. But the real system is 2 days far from this condition. So it would be a second indication that, in fact, in the system, we do not, the fact that we have 7 degrees, so the fact that we are more or less close to 0 is just a coincidence, and in fact, the Laplace angle would be circulating in this system. Another system is HR 8799. This one is very interesting because it has been observed by imaging. So we can see the 4 planets. In the others, we have only indirect indications, either by photometric analysis of making the photometry of the light of the star, or then making taking spectra of the star to see the radial velocity. In the case of HR 8799, no. In this case, we have the image of the 4 planets. This is a problem. This system is very young. The age is about 30 million years. The planets are very big, and they appear well in this image because these planets are yet bloated. They are not yet being completely reach the more compact form. They are still in the contraction phase. When we look at these planets, okay, the periods are close to 1/2 and 1/2, all of them, but not exactly 1/2. The differences are very large in this case, if you see the numbers. But we must to take into account this. Look at the absolute values of the periods. The first one is 42 years. The fourth one is 430 years. So this system has been discovered less than 15 years ago. So the quantity of observations that we have is very small. So we do not have a good knowledge of the period. In some studies done by Godzievsky and Mikashevsky, they have shown that it's not impossible that this system be in a 4-planet resonance. So we have exactly 1 to 2, 1 to 2, 1 to 2, 1 to 2. Excuse me, 3 times 1 to 2. So that when we can force this condition and obtain solutions that reproduces more or less well the observations. However, it's interesting to see also the results obtained by Fabrici with a coplanar model, where the only constraint is that the system is stable. That the numbers are more or less the ones that are here, and showing that there is a problem to be studied. Another system, STOI 178. This system has been discovered by the Space Telescope TESS recently. We have 6 planets forming a chain: 3 to 5, 1 to 2, 2 to 3, 2 to 3, 3 to 4. And if you look at if you compose the mean motions following the equation Kn minus K prime n prime, you see that, okay, the first one is a little bit more larger, but the others are 1.38, 1.37, showing that at least the three last ones, if we take a system of coordinates that is rotating, the system follows the system in a very exact way, forming a periodic solution. This has been studied by several people. Leleu has been the main author of a discovery paper full of other authors that have contributed to this paper. And one part of the problem has been studied by our colleagues of the EMCCE, mainly, I think, Robutel and others. And we have 3 triple resonances in the system. Look, the angles are shown in the right figure. You see that the variation is very small. So even in a time that is about 10 million years, the system remains with these angles in. Sorry, this figure is, the numbers are very small. I forget putting my glasses. 100 years, this figure. But this system remains stable a long time. And when we study it using the frequency map of Lascar, we see that, look, mainly the figure of the right side. In the figure of the right side, we have the vertical and horizontal strips correspond to the regions of two-planet resonance. And the small ellipse in the center of the figure and the diagonals corresponds to resonances involving 3 planets. You see that the resonance of 3 planets, in this case 4, 5, 6, which appears exactly in the center, in the middle of the figure, is very, very stable. It corresponds to stability indicators that correspond to very regular motions. Let's now talk about Apsidal Corotation resonances. This is a subject that is a little bit, is less recent than the authors I have just shown. These are the resonances corresponding to 2 planets, and which should be present in some cases, because when we have a resonant chain 1 to 2, 1 to 2, forming a Laplacian resonance, for instance, in the case of the satellites of Jupiter, Io and Europa, they are located exactly in a resonance of this kind. It's a 2-body resonance that corresponds to a periodic orbit. These resonances have been studied following several directions. One of the approaches was followed mainly by John Agidemetriou and by our colleagues from Thessaloniki. that consists to look at the periodic orbits of the 1+2 problem and to look which are the initial conditions that corresponds to the exact resonance. There are numeric constructions with ad hoc dissipation that have been done by myself about 20 years ago. And there are also the study of equilibrium solutions of the average Hamiltonian that have been done mainly by Christian Bourget and Tatiana Mischenko in São Paulo. We have done number 2 and number 3. The two last approaches were done more or less simultaneously, and more or less it was an hazard that we were both working on the same problem, even if we were following different approaches. Here is the result for the 2-to-1 resonance. Okay, from the 3 approaches, I told you, G. Demetrio, myself, and Christian and Tatiana, I will prefer to tell about mine because I am more fluent on it than on the others. So, what was my approach? My approach was to take 3 satellites around a planet and an interaction, a tidal interaction between the first planet and the star. I will recast this sentence because we are working with planets, we are working with satellites, and I am mixing the words. In what I have studied, the central body was Jupiter, 3 satellites around Jupiter. So there was a tidal interaction between the first satellite and Jupiter, and this interaction gave rise to a convergent migration. So Io was pushed away from Jupiter. So he was going close. He was going to be close to the others. What happens? Initially, look at the first side, the right side, the right side figure. You see that the angles in this figure are the critical angles. You see that there is one Perijov that is more or less near 180 degrees, and another one near 0 degrees. If you look at the figure, you see that there are black here. They are not captured there. They are rotating in this region. At a given moment that is dubbed as A in this figure, we see that one satellite is captured in an orbit with a perihelion at 180 degrees, and the other at 0. Okay, it is here, exactly. After a certain time, this one that was captured in this condition, the eccentricity goes very close to 0, and when it becomes again an ellipsis, the perihelion the pericenter is on the other side. The two in this region, the two satellites have the perihelion exactly oriented on the same direction, in the same direction. And then later on, when I continue pushing and continue forcing the satellites to be close among them, then what happens is that they abandon this situation and the angles became different from 0 to 180. We still have a frozen angle, but an angle different from 0. Here are the figures that show what I am wanted to show. First, on the top, the symmetric Apsidal resonances, in which the conjunctions happens always on the same line. The conjunctions happens on the line where the periaxis area, the one pericenter here, the other pericenter is here, Oh, the other case, when there is an inversion, both are on the same side. Here, the two pericenters are here. After that point, when I push them more close, they become more elliptical, and they abandon this position to another one that is asymmetric. This is still a periodic orbit, but in this periodic orbit, one pericenter is here, the other pericenter is here, and the conjunction line of the two planets, when the two planets are one in front of the other, they are in this position, more or less. The same here in this other picture. What we observed at that time is that Gliese 876, the two planets that the only ones that were known at that time, were very close to a periodic orbit. Look at this figure. In this figure, we have the two axes, the eccentricity of the inner orbit, E2, the eccentricity of the second orbit. The lines are the characteristic lines that correspond to the periodic solutions for different ratios of the two satellite masses. In the case of Gliese, the mass is about 3 times. The mass of one satellite is about 3 times the mass of the other. The mass of the outer one is larger than the mass of the inner one. And the eccentricities are known. The inner one is about 0.27. It is here. And the other one is about 0.03. It is here. So Gliese 876, the planets 2 and 3 are in an apsidal resonance. They are moving very close to a periodic orbit. This is the same for the case of the external case. The external case is when the body that is out, the outer body is much larger than the inner one, and we have in this case the solutions are mainly, most of the time they are asymmetric. The symmetric solutions correspond to the basis of this figure, to these lines, but you see you have more or less the differences between solutions, if their mass ratios are different, are very small. They are mainly great. The differences are mainly larger in the case where I have asymmetric solutions. Here is a similar figure now obtained by Michenko and Boget. In this case, it corresponds to the 3-to-1 apsidal resonance. The characteristic curves of the periodic solutions in this case were constructed using the Hamiltonian of the system. And for different ratios of the masses, we have these lines. I will not describe the details of these lines, but there are stable periodic solutions, unstable periodic solutions, cases in which the inner one is larger, cases in which the outer one is the largest one. And I stop here this conversation, and I'm ready for the questions. Thank you.
So thank you, Sylvio, very much for this very interesting talk. Are there any questions from the audience? Please just turn on the microphone and speak.
Christoph, can I make one?
Yes, please.
Well, thank you, Sylvio, for this nice talk. Apsidal corotations, we have though also when there is no resonance, mean motion resonance. I mean, this is very, very classical situation. So what is so special about the system being in mean motion resonance and in apsidal corotation? So there is something that really diversifies the case where the system is in mean motion resonance or not, as far as the apsidal corotations are concerned.
Sylvio?
Okay, no. My microphone was off. Okay, these are two different problems. In the case that we are called apsidal corotation resonance, we have the resonance and the alignment, or at least the freezing of the two pericenters. In the case you mentioned that you are far from the resonance and the circular resonance, we just have a combination of two circular motions around different centers. And this can, if one is very small and the other is big, this can have a small vibration, a small oscillation, but this does not correspond to a bifurcation in the phase space. While in this case of the apsidal corotation resonance, this is indeed the center of a region of regular motions. So the center is a periodic solution of the system.
May I ask a question to Sylvio?
Please.
Okay. Sylvio, at a certain point of your talk, you said that you studied the model by introducing an appropriate dissipation. Can you tell a few words more about this kind of dissipation that you put in?
Well, the idea was to have one central body and two orbiting planets, or one central planet, two orbiting satellites. There is a lot of echo.
But we can hear you.
The system evolved adiabatically, very slowly. We introduced a tidal interaction between the first planet, the first satellite, the inner body, the inner satellite, and the central body. And so we were squeezing the three satellites very smoothly, very slowly. And he was growing, he was evolving from, okay, I don't have a periodic solution because I still have the dissipation working. But if I let me recast the sentence. I am squeezing the system, okay, and it is evolving. If in a given moment I stop the squeezing, I stop the dissipation, it would be in a periodic orbit with those parameters. If I continue squeezing, okay, I am evolving from one solution to the next one. So I am able to make to draw the characteristic curve of the periodic solutions. Sorry, I was not very clear. Did you understand me?
Yes, I understand more or less, but what I'm trying to understand is this point. It seems that if you consider some kind of dissipation, tidal dissipation, for instance, there is the orbits corresponding to a periodic situation, resonant situations, are in a sense privileged, in the sense that there is some I don't know which one. It is just a very rough, a very immediate idea that I cannot present in a clearer way. But it seems as there is a mechanism of dissipation which is minimized by the resonance situation. So in some sense, dissipation disappears when the resonance is reached. This reminds me somehow also the behavior of quantum systems, where there are privileged states that are probably strongly connected to the fact that there is a resonance, which plays this kind of privileged role with an external mechanism or internal, I don't know, of dissipation that makes the system to collapse there. And in the case of a quantum system, the typical time is so short that we can observe it very easily because the equilibrium is reached in a very short time. This is not the same for planets or satellites, but we can observe it if the system has evolved for a sufficiently long time. This is just an idea that I put forward in this way. I don't know if you have any comment.
Yes. Indeed, look, it's very usual to make experiments, to make numerical experiments, where we introduce artificially an adiabatic variation of one same major axis, for instance. Okay?
Yes.
We introduce an adiabatic variation of the same major axis, and this has exactly the same effect as putting a tidal interaction. The tidal interaction was just because at that time I was just interested in problems with tidal interactions. So, but you can look at this just to a system of two satellites, where the first satellite, the same major axis increases adiabatically by any reason. Okay, I just put something in my code to make it increasing very slowly. So the dissipation itself does not play any role.
Okay, thank you.
Do we have further questions? Please just turn on microphone and speak.
Christoph, may I make a question?
Yes, please.
Sylvio, thank you for the nice talk. Giuseppe speaking. Can you make some comment about the tidal model that you have chosen in the dissipative scenario? I mean, do you consider a slow central body or a fast central body with respect to the period of rotation?
Okay, in this case, okay, the model that was used, the best model that we have to use in a code is the model that has been proposed by Mignard. So in the code that I have used that resulted in that figure, I have used the force that is given in Mignard's paper. Okay, you are correct, remembering that the speed of rotation of the central body is very important, because if the central body is rotating very slowly, instead of squeezing the system, I will be making it larger. Okay, the inner body will fall on the central body instead of being pushed away from it. In the case of that I have in this special case that I have studied, Jupiter and satellites, the period of the first satellite is 1.7 days, and the rotation of Jupiter is about 9 hours. So Jupiter is rotating with a speed much more larger than the orbital motions, the angular orbital motion of the two satellites.
Okay, thank you. So your scenario is more adapted to a planet-satellite system rather than to a star-planet system.
Well, in the case, in the case of a planet, in the case of planets, we have both. We have cases in which the star is rotating very fast, and there are cases in which the star is rotating very slowly. This is very tricky because this depends even on the spectral type of the star. If for a big star like a F star with a mass 1.5 solar masses, we many times have a star rotating very, very fast. Very fast, maybe periods of 2 days, 3 days. While if this is a solar type star, it was fast when it was created, but it's now rotating as our sun with a period of the order of 1 month. It's very interesting, for instance, in the case of TRAPPIST. In the case of TRAPPIST, some people that, as they studied the tidal interaction of the TRAPPIST, when these planets were formed, the star was rotating very fast. So the tidal interaction with the inner planets was squeezing the system, was pushing the innermost planets away. But because of the stellar wind that is making that a leakage of the angular momentum of the system, the star becomes rotating slowly and slowly. So currently the star is rotating with a speed that is between the orbital periods of the second and the third, more or less. So it is no longer pushing away the innermost orbits, but is the innermost orbits are now falling on the star.
Thank you, Sylvio. Very, very interesting remarks. Thank you.
Further questions? Sylvio, I have a question. You mentioned that you included the tidal interaction between just the star or central planet and the first moon or first planet. Why is it sufficient to include just the tidal interactions between the innermost one? And does it mean that we could neglect the effect on the other contribution, also to the other planets?
Okay. Look, the gravitation is a force that goes with 1 or over R2 square R square. In the case of the tides, this is a reflex action. So there is an action of the satellite over the planet is 1 over R2 that responds acting on the satellite with another 1 over R2. So we have a force in the inverse to the fourth power of the radius. In general, the tidal effect on the second orbit is much smaller than the one on the first orbit. Okay, and usually it can be neglected. But in the case that I have studied, I was not interested exactly in the tidal interaction of the planet and the satellite, but I was just using it to squeeze the satellites one against the other.
Thank you, Sylvio. Do we have further questions? Please turn on just the microphone and speak.
Well, I have one.
Please.
So let me thank you, Sylvio, for your nice talk. And well, at the very beginning, you showed the difference in terms of degrees per year. The difference between well, associated to the resonances of the mean motion angles. Okay, well, it seems to me that it should be in the cases you have shown of the order of the secular frequencies or the secular periods. Depends on what you are measuring. Well, and since when you expand the terms in the Hamiltonian, you have the so-called D'Alembert rule. So in the resonant angles should be included also terms that are, say, a multiple of the argument of the periastron, or a multiple of the longitude of the nodes. So you didn't talk at all about that. So am I right in the sense that, okay, we could have a perfect resonance by including also these secular frequencies, or not, in the sense that they are too small in order to compensate the difference of the mean motion angles?
Okay. I don't remember the numbers by heart, but I am sure that for the solar system, degrees per year is much larger than the actual motion of the
this is for
pericenter.
sure.
In the case of the resonant motions with exoplanets, I had not degrees per year, but degrees per day.
Okay.
Okay, because these are very compact systems that are moving very fast. Okay, but what happens? Forgetting about the figures themselves, what happens is that in the case we are close to a resonance, the resonance creates a forced eccentricity and a forced motion of the axis of the ellipse, which is much larger than the proper ones.
Okay.
Okay. So in the case you are far from the resonance, we just have the motion of the pericenter is equal to the proper motion of the pericenter. In this case, in the case we have a resonance, we have a kind of linear system of first order in which non-homogeneous, in which the motion, the proper motion of the pericenter is given by the characteristic roots of the homogeneous part of the equation, and the forced eccentricities are given by the terms on the right-hand side, on the non-homogeneous part, which will lead to divisors that correspond to the resonance, and then they will become very big. Okay? Because they have small divisors embedded in them. So in that case, like in the case of IO and Euro, okay, the forced motion dominates completely the motion of period. We see various sites, including some sites of NASA, where they say that, okay, it's written that the motion of the pericenter of Jupiter of Io is 0.00001. Wrong. This is the proper perihelion. The forced perihelion is moving 100 times faster. And this one dominates, and this one makes the real move, the observed perihelion, the real perihelion of the Earth will move with the forced velocity, not with the proper, the one given by the proper one, the characteristic roots.
Okay. Okay, thank you.
Okay. I have sent to Alessandra some time ago the link to my old book of 1980 on the Galilean satellites that I have. I was sick in past year, not because of Corona, but because of quarantine. Okay, and I spent 6 months not being able to work. In that time, I take my old book and I retyped it in LaTeX. So now it's much more nicer to read than it was before.
Okay.
Alessandro has the link.
Okay, so we'll have a look to that.
And there, this question of the proper eccentricities, forced eccentricities, and osculating eccentricities is completely discussed.
Okay.
Not merit of mine, I took everything from Tisserand.
Thanks.
So are there any further questions from the audience? Also writing it into the chat window if you like, if you prefer, we can read it. So are there any questions? If not, let us thank the speaker very much for this very nice talk. Thank you very much, Sylvio, for having the time to give us the insight into the problem. Thank you.
Well, don't know, in times of quarantine, what we have a lot is time, you know. So I am very glad. I am very glad talking to you today. I just apologize not being at Rome to give you in person this talk. This is my only regret. Thank you very much for being there.
Thank you, Sylvio.